So all these links from the cloud, where you have all, say, the raw ingredients, down to protoplanetary disks, down on early planets, is what really motivates my research. And we would like to make some links to really follow the history as much as we can. So we will start, now I will accelerate a little bit. So we will start from dark clouds and prestellar core. So I define to you what what these are. Some basic, like 101 astrochemistry, so then everybody can follow me later on. I mean, it's really easy, nothing complicated. And then I will just say a little bit about the fractionation, so the enhancement of deuterium in molecular material, and also the enhancement in 15N, which is actually a signature of this pristine material that is also present in our solar system today, that links to what we see in the early phases of star formation. Something about complex organic molecules, and finally the formation of protoplanetary disks in our view, because of course there are also other views. So our Milky Way, this is, you know very well, this is oh, actually I have an optical image I was talking before about. So this is the optical view of our Milky Way, and you can see lots of dark lanes, and this is where molecules reside and where new stars and new planets are actually forming right now. And of course, as you can see with the optical, it's very hard to actually say anything about these clouds. But of course, as soon as you watch a molecule, and in particular, of course, the CO, which is the most abundant molecule after molecular hydrogen, that unfortunately is not possible to detect at the temperature and densities of these clouds, which are about 10 Kelvin and a few thousand per cubic centimeter of H2 molecules. But you see, CO is very bright where the light is actually completely blocked. So we have here gas and dust particle. And for example, you can see, and the dust is cold. In fact, you can see very well the structure of these clouds, for example, with dust continuum emission at 500 micrometer. This was a picture taken from Herschel. So here you start to see some regions that are quite bright. And these are the location of future, say, star formation. And this is what, in fact, we have studied a lot. This is, I consider this as our laboratory in space, because it's a very bright prestellar core. It's a dense fragment of a larger molecular cloud, which has evidence of contraction motion. So we know that it's out of equilibrium and is going to form a star. So it's an ideal place to study the initial conditions of star formation. So we have studied this since many years. We know that, for example, at the peak of the millimeter continuum emission, where the center of the core resides, many molecules are gone from the gas phase. They reside on the surface of dust grains, and we can observe molecules that contain deuterium. Deuteration becomes a very important process. I will show you. And so deuterated molecules, in fact, are really good to trace cold and dense material. So if you want to do like a blind survey in deuterated molecules, where the deuterated molecule is bright, is where you have dense and cold and probably contracting core. Around this zone, we get into the more classical, say, ion neutral chemistry, dark cloud zone. And then, of course, we have the outer edge, the merging with the more atomic phase of the medium. What we found more than in 2007, this was work with Antonio Crapsi, our student in Florence at that time. We measured the temperature of this dense core, prestellar core, and with the VLA, because with the single dish it was very hard to actually say something about what was happening inside this core. And with the VLA, we found the temperatures that were close to 6 Kelvin in the center. So the temperature keeps decreasing. Of course, the density is large, so you keep, say, screening the interstellar radiation field more and more. and then the dust really cooled down at very low values. And this, by the way, is the single dish observations that was taken with Effelsberg. So in this case, you have molecular freeze-out, because molecules, when they hit the dust grains, they don't have energies to go back in the gas phase, so they form very thick icy mantles. And this produces deuterium fractionation. Again, I will explain why there is this link in a minute. Let me just show you one more thing, why molecules are useful. So in the same cloud, in 2012, we detected the water line. This was 13 hours of Herschel time. So I was getting actually very nervous because the line was so faint that we couldn't see until the last minute. So anyway, we saw it, and the beautiful thing about this line is that it shows an inverse P Cygni profile, so we can model this with infall. And this emission, so because the water line, this is the ground state line of water, ortho line, the critical density, so to excite this molecule, you need the densities that are above 10 to the 6 per cubic centimeter, H2 molecule per cubic centimeter. So this emission must come from the center of the cloud. And then the absorption comes, of course, from all the material that is between the center and us. So it gives you this relative motion that is just the contraction motion. We could reproduce very well with our model that we already had from other molecules. But anyway, the main result from the water is that we could say something more precise on the for example, on the contraction motions in the central 1000 AU astronomical unit of this cloud. We measure the total mass of water vapor. You see, it's not much, because most of the water is in the solid phase. So we have like half Earth masses. However, to reproduce this amount of gas phase water, we had to put almost 3 Jupiter masses of water in solids. So you have to start thinking about these dust grains with just very thick icy mantles, and many of them will really reach the protoplanetary phase. And cosmic rays are important to reproduce this. Without cosmic rays, we couldn't reproduce what we were seeing. They say, why cosmic rays? Because cosmic rays, unlike photons, they just don't care about how dense your cloud is. They just go through, and while going through, they excite H2 molecule. H2 molecules are excited to, say, higher levels, and then they fluoresce back and emit UV photons that actually can photodesorb molecules. Not at the high level, is like 10,000 times less intense than the interstellar radiation field, but it's still enough that, you know, it's better than nothing. And it really helps to make some of these molecules go back in the gas phase. Very tiny little bit. Just quickly, because I think this is important to stress how molecules are, you know, why we were observing this molecule, why we have to spend all this expensive time with Herschel to do these observations. It's not just the fact that you can measure the water, but as I said, you can measure the dynamics. And in fact, in 2005, with Eric Quito and Jonathan Rawlings, we were able to use the ortho H2O and also the CO, another CO line, to discriminate among, say, the most classical model that have been proposed for the contraction of dense cores, like the singular isothermal sphere. This goes back to Frank Shu, 1977, or the Larson-Penston contraction model that was in the late 60s. So this is a density profile predicted by these two models. In blue is our model that is the model that is required to reproduce, say, the line profile that we see, and this is we call quasi-equilibrium, because we see this relatively massive cloud that is contracting, but is subsonic. The contraction is subsonic. So you see that from the density profile, there is no way that we can discriminate between these various models. But if we look at the kinematics, this is velocity as a function of radius, you see that the predictions of the three models are really large. So thanks to molecules and to the fact that we can test the kinematics, we could put some constraints on the dynamics. So you can see here, again, the water line with this square, and this is the C18 1 to 0 line, and the various panels here shows the SIS, LP, so Larson-Penston, and this quasi-equilibrium. And you can see that only with the quasi-equilibrium is we could reproduce. So SIS and LP are definitely not good for this specific cloud. So we could easily rule them out. And we need always at least, say, 2 lines because the CO is measuring the envelope, the water is measuring the central part to be able to model. More recently, this is the paper that appeared a couple of weeks ago on AstroPH. We tried for several years to actually detect prestellar cores with ALMA. Because why you want to do that? Because then with ALMA you get rid of the extended emission. You're just concentrating the central part, and then you can basically look at the kinematics and make constraints for models that are currently done, that say models of star and protoplanetary disk formation. Things are not easy because these objects are big, are very big for ALMA. And if they are not enough centrally concentrated, you are not going to see anything. And now we have definitely a proof of that. So, however, this L1544 in Taurus is actually very centrally concentrated, and we were able to see also with the 12-meter array. This is the map that was done without ACA, so without the compact array or total power, that actually there is no total power for the continuum. So we were able to see this structure. This is the ACA compact array, and this is the combined. So of course, one thing that you notice is that we see structures, substructures here that at the beginning we were very excited about, because of course everybody wants to know how multiple stars are formed. But in fact, after I think more than a year of modeling, especially thanks to Jaime Pineda, we realized that these substructures are actually consistent with artifacts due to the interferometric observations. So we are not claiming any substructure here, although we will probably apply for new time for more sensitivity. But what we can see is that for the first time we can resolve the inner structure. So this core is 8 solar masses. What we are left with ALMA is 0.1 solar mass. And this is a little thing that I didn't know how to call it, so I call it a kernel. And it's where the material is at the moment inflowing and is going to actually form something there. I don't know what. I mean, if it is a single or multiple star. But we put some constraints on this. And the other thing we did in this paper is to make comparison with the predictions. So Bo Zhao, who is also at MPE, he's running non-ideal MHD simulations. And he started with the cloud that has characteristics similar to the one that is surrounding L1544 with similar, say, rotation velocities, similar densities, and then let it contract. And this is the simulation. So you see, if we consider magnetic field, even when the central density here is 10 to the 7 per cubic centimeter, we do not have any fragmentation. You need to get rid of magnetic field to start to have fragments. But in our case, we took this for the specific slide, actually. I also have the HD, the hydrodynamics, but I just to focus on this, because this gives the best results. So with the non-ideal MHD, magnetohydrodynamic, starting with these relatively diffuse clouds and contracting, arriving at a peak density of 10 to the 7 per cubic centimeter. We have this is the simulated observations of the cloud when it reaches a peak density of 10 to the 7 per cubic centimeter. Now, what we did, we also stopped the simulation a little bit before, 5 times 10 to the 6 per cubic centimeter peak density, and you don't see anything. So basically, this means that to detect prestellar cores with ALMA, if you want to detect them, you will only detect those that are at very advanced dynamical stage, so very close to star formation. You're not going to detect dense cores or starless cores, and that is why there have been no detection in all previous surveys that were done. Right, so let me now switch to the basic astrochemistry, because I wanted you to understand why we have this deuterium fraction and why this can link to our solar system result. So, okay, here I put some key ingredients. This is B68. This was the famous image from João Alves in 2001. Key ingredients, dust. The dust is needed, first of all, to make H2. Without H2, we don't go very far. And then we have molecules that, of course, are forming as a consequence. So once you form H2 in molecular clouds, and this happens on the surface of dust grains, the other ingredient you need are the cosmic rays. Cosmic rays ionize the H2 molecule. Okay, I thought there was a question. No, okay. Ionize H2 molecules, and once they are ionized, actually 97% of the time that the cosmic ray hit H2, it ionizes H2, and then produces this electron that contributes to the heating of the cloud. And what happened with H2 plus? Well, in a medium which is rich in H2, you can forget about anything else. H2 plus will just react with H2 and form H3 plus, just because of the enormously larger abundance of H2 molecules. H3 plus is the most important molecular ion in astrochemistry. Why? Because it is an H2 molecule with the not very bound proton, and this not very bound proton can be given away very easily, and this, once it does that, it initiates the chemistry in the interstellar medium. So for example, if it encounters an oxygen atom, it will give the proton to the oxygen and form OH+. Once OH+ is formed, it will immediately react with H2. These reactions in chemistry are called abstraction reactions. So you get the one hydrogen from the H2. You break the bond of H2, which is easy because this is an ion molecule, ion neutral reaction, so the rates are actually relatively fast. And you get the hydrogen more and more until you cannot get it anymore, because there are no valence electrons and you cannot add other hydrogen. And then there are electrons that, of course, dissociate the final product, and you see you form water, oxygen, even molecular oxygen. On the other hand, if it encounters a carbon in the interstellar medium, it will start the hydrocarbon chemistry, very similar to the oxygen chemistry. And now here, this is the route to HCO plus and CO, very well-known molecules. So there is also surface chemistry, and this is our, give us so much headache because we don't know anything about. Well, we try to understand, but every time we understand something, there is a new thing that we don't understand, and so we have to keep calm and do one little step at a time. Basic thing that I would like you to understand here is that if this is your dust grains, which is definitely different from the real dust grain, which is not spherical, we have to consider accretion. So you have to take into account the thermal speed of the molecules or atoms. For example, if you have a heavy atom like a oxygen, it will tend to just sit there, don't go anywhere else. But then a hydrogen comes, and the hydrogen has been also seen in the laboratory that can quantum tunnel. So it can move very quickly around. So we have accretion. This is a slow process in these diffuse regions. On a typical molecular cloud, it takes a few days. Have to wait until one thing goes down on the surface a few days. But then if the hydrogen comes, the hydrogenation will be extremely fast. Hydrogen can sweep over the grain in a very small fraction of a second, because even at very low temperature, it doesn't matter quantum tunnel, it doesn't matter temperature. So when that happens, it means that we have association reaction, and most of the association reactions are H plus H, so it forms H2. And then it can form, H can hydrogenate other elements like oxygen, carbon, nitrogen, and also CO. And you see that oxygen will end up into water, so you are saturated your molecule. Carbon go to methane, nitrogen to ammonia, and CO to methanol. And this is in fact what we see. Okay, so hydrogenation is efficient, and this has been sorted out, I think, quite a long time ago. But now we want to know more. We want to know bigger molecules, and this is the problem, and we are still struggling to understand that. So you have to, I like always to imagine things very much, and this is, I think, a picture that helps to understand. So you have to picture in your mind this complex structure of the dust grains, many of those in space, and then hydrogen atoms that just land, and once they land, they sweep around, and if they find an element, they will just react with it. Very, very reactive. So in a dense cloud, you have to imagine your silicate or carbonaceous material, so the, say, bare grain, surrounded by quite thick mantles, mostly made out of water, but also CO and CO2, ammonia, OCS has been seen, and methanol also has been seen in ice form. So let's now talk about deuterium fractionation. Why it is important and why do we care? Well, we care because also our oceans are deuterated. So this is the D/H ratio in the protostellar, or say interstellar medium. And this is basically set by the Big Bang. So D/H, 10 to the minus 5, 1.5, something like that, some variations. But in any case, this is the abundance of deuterium. Then, if we look at the H2O in our oceans, and we take the HDO, and we take the ratio, we see that the D/H is 10 times larger than the cosmic abundance. Then we look at the comets, and that's even larger. And in fact, this is a 67P, the comet that was visited by Rosetta, and you see it has a very precise value here, and it is actually one of the largest that has ever found. I would like you to notice that the carbonaceous meteorites, the ones that also contain these super complex organic molecules, have a D/H ratio just on the value of Earth oceans. So in fact, there are many people claiming that in fact we probably got the water from these carbonaceous chondrites, but this is still, say, not everybody is agreeing on that. So, deuterium fractionation, how does it happen? The first thing is, again, you see we have our H3 plus that now reacts with HD. HD in a molecular cloud has the same abundance of the deuterium in an atomic cloud, so we are like at the 10 to the minus 5 level. But this reaction is exothermic, so, and the exothermicity is relatively high for a cloud that has only 10 Kelvin, so it cannot go back. So with the time, you start to accumulate H2D+. This was actually sorted out in the 70s by Watson. And then later on, Dalgarner-Lepp in '84 pointed out the fact that without considering the freeze-out, say for some reasons, the neutrals like CO and also oxygen that can destroy H3+ and H2D+ are gone from the gas phase, and this could be possible, for example, if you are also in a, say, early universe type of chemistry, because there are not many metals, or in any case in a low metallicity environment, but also in our prestellar cores that are heavy, where these molecules are highly frozen. The problem is that you have the following. So once you have CO freeze out, the destruction rate of both molecular ions lowers down because you don't have this important destruction partner. And you have a higher H2D+ formation rate because you have more H3+ that can proceed with this reaction. So the sum of the two gives you a larger H2D+ or H3+ abundance, and they pointed out that in the 80s. So what we see is that, well, CO actually in the center of this prestellar cores is 99.9% gone from the gas phase. So you really have a lot of material on these ices. So this is the H2D plus that in fact we proved in 2003 that yes, it is strong, because it's exactly going from this previous work, Watson et al. And we can understand that in the center of the prestellar core, this is again L1544, we found the strongest H2D plus line that was ever found before. It was not a discovery, was already found in another region, but previous people didn't look at prestellar core, they look at the star-forming region, and this is where we should look if you wanted to study H2D plus and this light ion chemistry. So here, I told you about this step here, H3 plus until H2D plus. However, this can go on until you actually form a completely deuterated molecular ion, which is D3 plus. So you go through D2H plus, which has been detected, both ortho and para form, D3 plus that we are trying to detect, but we have not yet detected. It's difficult because this goes into the infrared, so like 5 micrometers. So, you know, in this very opaque region, it's hard to see. But in any case, we will keep trying. So what happens once you increase the abundance of this deuterated molecule? Well, first of all, when they encounter, for example, CO, some of them will give hydrogen, but especially the doubly deuterated will also give deuterium to the CO and form DCO+. So that is when the gas phase species like N2H+, this HCO+, and ammonia can get their deuterated deuterants and become deuterated. At the same time, when they dissociatively recombine with electrons, these molecular ions can also react with electrons, which destroy the molecule. You increase the D/H atomic ratio in the gas phase because you produce atomic deuterium in the gas phase from these molecular ions. And these deuterium atoms compete with the hydrogen atoms to saturate the molecules or the elements that are in the surface. So you can form deuterated water, you can form deuterated formaldehyde, deuterated methanol through the deuteration of CO. And in fact, not just singly deuterated, but even triply deuterated methanol and ammonia have been detected. So it's really a super efficient process. And it's so efficient that, in fact, if we compare to what we see in our solar system in the pristine material, is way above. So, for example, here is a compendium of papers. This actually was done at the time when we had the Herschel observations. So you see that this is water, H2S, ammonia, and then we have also formaldehyde and methanol. We have here the singly, doubly, and triply deuterated forms of the various species. And of course, you can see immediately that, yes, water can be deuterated, but only slightly doubly deuterated. And then what we have that the organic molecules are much more deuterated than the water. And I think we can finally understand also why this is the case. So why water is less deuterated than the organics. The reason being that this is just, as was explained by this paper by Stéphanie Cazot and also Takei in 2011 and 12, it tells us about this history of formation. And in particular, when you are at the outer part of the cloud, you just form a tiny little layer of, say, water ice. Water ice is mostly actually becoming thick in this outer, say, edge here. So outside the cloud, it's very difficult because you have too many photons that photodesorb. Here you have the thick water ice, but there is not much freeze out of CO, so the deuteration is not very high, so you don't have many D atoms in the gas phase. And so you cannot get much deuteration, and also definitely not much deuteration of CO in methanol because there is not much CO on the grains. But it's at the time when you get to these very dense regions that the deuteration happened. And at this point, most of the water is already gone. So most of the water ice is formed in these earlier phases here. And later on, you have mostly CO freezing out, and this is where the methanol gets deuterated. So we can explain why we see organic molecules that are more deuterated than like water. What happened in our solar system? So if we look at the, again, carbonaceous chondrites in our solar system and the D over H, if we look at the D over H in hydrosilicates, hydrated silicates, so these are the, basically it tells you the deuteration of the water in this material, we see that the D over H is about, few times 10 to the minus 4, very close, as we saw before, to the deuteration of the water in our Earth. What about organic material? So if we look at the organic matter in chondrites and also in the interplanetary dust particles, we see that the D over H can actually get higher, much higher than the one found in the water. So it's consistent with what we see in star-forming regions. And we think that this is due, again, to the history of, say, going from the diffuse cloud to the dense cloud. So for me, this is a kind of signature telling me that there is some material, of course not very much, some hot spots, in fact, in these slices of meteorites where we see this enhanced deuteration that could be a relic. For the 15N fractionation, things are a bit more complicated, and in fact, I will not go into the detail. I just show you what we have. This is a very nice picture that was published by Healy Blunt in 2013, where we have again our solar system material and then comets and starless cores. The thing that Healy Blunt and others notice is that the 15N enhancement are different depending on the type of molecule that we have. So if we have a CN type of molecule, like a nitrile molecule, like HCN and CN, we have a significant enrichment of 15N. In case of ammonia and also N2H+, this is not the case. So there is a differentiation. By the way, if you are curious to know, for example, what has been found for protoplanetary disk for the 15N enhancement, you see that these values are very large compared to what we have, for example, in our Earth, which is 270, 14N over 15N. Here we go down to 80 and 160, so very large fractionation, very similar to what we see also in starless cores. What happened in our solar system? In our solar system, it's a little bit messy. So we have 15N excesses that are found even as, in this case, you see this is 14 over 15, 65, so a high value, large amount of 15N enhancement in some, again, in some hot spot that do not necessarily correspond to the deuterated hot spot that I showed you before. And look at this. This is the 15N fractionation. This is a relatively recent paper where they found that in this meteoritic material, 15N fractionation is larger in CN groups like HCN and molecules that contain CN compared to, for example, this NH2 type of molecules, functional groups. So ammonia, and again, we can put here also N2H+. And it's exactly what we see in space. So I thought that this was another nice link. There are some puzzles that this is my student that she measured. This took many hours of the IRAM telescope, 30 meter, to find these ratios in several prestellar cores and finding very, very low values of 15N. And this is still a bit of a puzzle, although there have been some attempts to explain. Anyway, let me give you a few words about complex organic molecules. I'm sure you are familiar with this beautiful spectra that have been taken by, say, Herschel and other instruments that show very rich spectra toward, say, star-forming regions. And of course, you know now that in star-forming regions, if the dust grains get very close to the protostar, or if they are shocked, they can lose these fragile ice mantles and release back the molecules in the gas phase. However, we see in fact, for sake of time, I want to skip these here. So we see complex organics already at the prestellar phase. And this is work by Taskun, Jimenez Serra, that was published in 2016 that showed that we have actually complex organics that are also seen in these star-forming regions in this cold environment. So how can it be? I mean, how can we, say, explain this? And in particular, you see here, you see HCN peak and methanol peak. I didn't explain the previous slide, but they're mostly intense, especially the oxygen-bearing organic molecules are mostly intense in the region where methanol is peaking. So this was explained by Anton Vasyunin. So now you can see the abundance with respect to total hydrogen as a function of radius of a prestellar core. These are abundances of various complex organics as a function of time. The model here stopped when actually the abundance of CO that we measure is exactly what we is in the model. And at this point, we can see that the peak of most of the organics is actually around a little bit. So this is the center of the cloud. We are at a distance that is quite similar to what we see in the methanol map. And this is due to the fact that the methanol peak and also the organic peak is at the location where CO started to freeze out catastrophically. So we have our own snow line, in a sense, in these prestellar cores. And here you have CO surfaces. The CO surfaces allow molecules that are formed on the surface to evaporate back in the gas phase upon formation, because some of the formation energy is used to go back in the gas phase, and this explains our observations. Of course, there are lots of big error bars, because again, there are still lots of things we need to understand about this surface chemistry. From the point of view of a comparison with comets, we know that there are say star-forming regions and comets have relative abundances of COM that are quite similar. This was shown in a paper by Beaver, who used the 30-meter antenna, but also by Altveg with the paper on the comet 67P, and Drozdovskaya et al. Okay, so in the last 2 minutes, I will show a few slides on the formation of the protoplanetary disk. So we are now using these prestellar cores as the initial conditions, and then we want to move toward the formation of the protoplanetary disk. Of course, for this, we need to know a lot of physics, because we have magnetic fields. So we have also ions that are attached to the magnetic fields. So we have dust grains that can maybe not really coagulated at the densities of the cloud, but definitely the very small grains can disappear because they also can freeze out onto the surface of bigger grains. There is lots of microphysics going on. And you can also form, and this is not yet be completely proved observationally, self-gravitating disks in the early phases of, say, protoplanetary disk. This is something, actually, there is a lot of effort going on now to try to find these self-gravitating disks in the class 0 stages. So this is the work led by Bo Zhao. And what he did, so he took the non-ideal MHD models that also Jiu Lee in Virginia was using, and Krasnopolsky, who was actually the father of the Zeus code that was used. We implemented some simple chemistry inside this code to follow more accurately the ionization, because as you can understand, it's very important in these non-ideal MHD models that follow the contraction of a magnetized cloud. And what he did is to consider different grain size distribution. So we took the MRN distribution as the first thing, and which includes also the very small grains, so dust grains, for example, pHs, but also nanosilicates that 10, 100 angstrom in size, and then also the rest of the MRN, Mattis, Ramps, and Nordziak distribution, and cut it, so truncate it to simulate the fact that this very small grain may disappear in this dense cloud. And what was found is that if these very small grains are removed from the simulations, we can form protoplanetary disk very easily. And why is that? Because these very small grains are very well coupled to the magnetic field lines. They drag the neutrals and the magnetic field lines toward the center. And when they do that, the presence of a strong magnetic field in the center is able to remove the angular momentum, and then the disk is not forming. So just to give you an example, this is the case where we have no very small grains, and you can see that in this particular case we have even an asymmetric outflow here, but the interesting that is actually forming a quite massive, well, almost self-gravitating disk in this case with some spiral arms. In the case of very small grains, there is no way that we are able to form a disk, and nothing is left except for some filaments toward the center. So just to give you here a little summary, it's some other type of disk. The interesting thing is that just changing a little bit initial conditions like cosmic ionization rate or angular velocity of the initial cloud, you can form very different type of systems that are actually found right now when we use powerful telescopes. So this is the Perez et al. 2016. You don't see very well here, but there is a spiral here, and this is what Bo formed. In this case where there is a very strong, actually quite strong magnetic field relatively to that one, you can form triple systems, and this is the probably one case in which they claim that was a self-gravitating disk, this Nature paper by Tobin, but actually, the presence of multiple stars could also induce these, spirals, or anyway, these tidal waves that can be due just to the presence of multiple stars. So just to finish, I want to show this beautiful work that also thanks to Jose Miguel here, and this is led by Felipe Alves. And this is an object that is in the Pipe Nebula, just to show you another geometry. So this is work that has been published in 2018, ALMA result, 30 AU resolution, where we see the disk here and some connections to the envelope, where in fact this material has been seen to infold down. And this is the map, so the continuum here, sorry, the light blue is the same as that, but this one is a specific channel of the CO line showing the outflow that is launched outside actually the edge of the disk. And this is also consistent with the models of Bo Zhao, where we have material, if we have material accreting at, say, larger scale compared to the scale of the disk, and all depends on the geometry of the magnetic field. If you have enough pinching in the magnetic field lines, and this was, you see here is 113 AU from the center, and the disk is about 80 AU. So this is work still going on with new ALMA data. So let me skip this. For the disk, I mean, we have not done much, so this is just to show you that also in disks there is a high deuterium fraction, and Karin Oberg and other people now have been seeing organics also in disks. Very difficult, but it is possible now with ALMA. And the main conclusion here is that when you compare the relative abundance of these molecules found in disks with the comets, again, you have the same values. So let me conclude. I would like just to, again, say that the prestellar cores are dense fragments of molecular clouds, so with central densities larger than 10 to the 5 per cubic centimeter. This is the way to discriminate if it is a prestellar core or it's just a starless core that may expand back or don't form a star whatsoever. Central temperatures are very low, 6-7 Kelvin, large amount of CO freeze out and deuterium fraction. And we saw that they also hosted the first steps toward prebiotic chemistry. There are large deuterium fractions, and we found them all the way from the original cloud down to our solar system, so which implies, of course, it cannot be the final word, so we're still working on that, but there is a hint that at least some of this prestellar ice is able to be stored and saved during the process of planet formation. The same is true for 15N, because in fact we see this 15N fraction that is higher in a CN species than in NH-bearing species, and this is the same if you are in the space or if you are in the solar system. We see exactly the same type of correlations, and also no correlation between 15N and diffractions. I didn't spend much time on that, but it's exactly the same. We don't see correlations in space, and there is no correlation, very little correlation between 15N enrichments and de-enrichments in meteorites. The complex organic molecules abundance in comets and also in, say, solar systems, star and planet-forming regions are very similar. The conclusion, this is actually coming from the Nature paper of Karin Oberg, solar system chemistry is not unique and similar at different times of evolution. So it seems that the basic chemistry is set at the very beginning. So that's it's like the revenge of the prestellar cores, in a sense. And so it's really important to, and it's easier to study these processes at these stages because there is no stellar feedback, and it's, you can at least attempt to understand the details. And then, of course, with the disks, depletion of very small grains, this was the biggest result from Bo Zhao. Very small grains enable disk formation without the need of any misalignment or other type of theories that have been found. So of course now the question is this true? Are these very small grains really gone? So this is something that we need to work on. So first of all, we need to have the self-consistent dust evolution algorithm to implement in this non-ideal MHD. But in any case, this tells us that it's really important to take into account the microphysics for dynamics. It sounds very difficult, but it's not. It's a lot of fun. So thank you very much. And sorry for being late. I'm late. I'm sorry. As usual. Thank you.
Time for questions, comments.
Thanks for the nice presentation.
Thank you.
But I am the only organic chemist in the audience, probably.
Ah, very good.
And then that is an adjective. Complex organic molecules are not. No? They are simple organic molecules.
That's true.
In fact, that is very dramatic and seminal, the last found, the amount of different organic. Then it will be better to speak about diversity.
Yes.
About diversity. And then in planetary chemical evolution, now is the question how this diversity, if reduced or depurated to only some relative few type of organic compounds and families, but they are different scenarios. And then I question that is really true. I realize now in these chemical cycles about hydrogen, there is cationic, the cationic hydrogen 3 and so on, and then I realized it must be true in strong ionization radiations because the electron is expelled. But in not so strong conditions, for example, in ultraviolet radiation, these cycles probably can be also constructed by radical reactions and not ionic reactions. That is, but could be expected. And my question is, nobody thinks that perhaps the deuterium abundance differs in similar cycles when you when you assume that the reactions are radical and not cationic? It could be a different. It could result in difference deuterium hydrogen ratio. When you think that the same cycles but not cationic.
Okay, I can try to answer a little bit. So first of all, you are completely right. In fact, we are in the process of renaming these complex organic molecules. There are suggestions that we should put an interstellar complex organic molecule, because yes, it's when we talk with chemists, we realize we shouldn't say that word. For the H3+, so the point here is that you have first to enrich the radicals. And to enrich the radicals, it's, from what we understand, it's very hard to do it without the help of the ions. However, the ions is not difficult to form, even if you don't have, like for example, in the center of this prestellar cores where the extinctions are really high, we talk about, basically there is no photon, very little photons, very, just very tenuous UV field produced by the cosmic rays, cosmic rays are present. Those are the drivers. So even if you are in a very dark and cold regions, you still have cosmic rays that ionize H2 and then you form immediately H3+. So that it's kind of easy to understand. What we also see, though, is that deuteration can also happen at higher temperatures, so warmer. For example, above 30 Kelvin, the reaction that I showed you before doesn't work anymore because it can go back. So, but we still see deuteration. And in these warmer environments, the culprit, let's say, is another ion. And this is the deuterated CH3+. So we have a CH2D+ that has, with the reactions with H3+ and say CH2, you have a higher exothermicity, so it can proceed even at higher temperatures. But in any case, for just starting with the radicals, then the question is how you enrich the radicals. And I think the best way is really through the ions. And so that's why we really need cosmic rays. Without those, I think we were not here. Yes.
Maybe it's more relevant. Thank you very much for a very inspiring presentation. At the very beginning, I was a bit surprised by you dismissing this so easily, the map made by the main array and by the compact array. And because that you're going to have new observations, but again, you'll have the same problem of combining the big array and the compact array.
You mean of the prestellar core? Yes.
I think it's very difficult to make that compact thing disappear. There must be some calibration problem relative to the two arrays. I mean, otherwise you see most of the VLBI maps and so on would be defective, would be wrong. I think that needs another, more attention.
Yes, definitely. I mean, this is I wanted to publish this data because, as you know, it's very hard to get time if you don't publish what you already have. This data, so this emission is very faint. So I think there is, of course, the sensitivity is not the best. We should have integrated them more, and we will definitely try to integrate more. However, what we did to prove or say disprove about this multiplicity, say fragmentation in the center of the kernel, is to make models. So we took like a cloud, smooth cloud, without any fragments, and observe it. So do simulated observations with ALMA with the same configuration, And sometimes you don't see anything, but sometimes you do see some of these fragments. So basically the conclusion was that with the quality of this data, we cannot confirm that it's true. So we have definitely to go back and do more observations. But this, of course, doesn't mean that previous work, you know, when you have a strong signal and high sensitivity, it's very hard to disprove. But in my case, you know, we are looking at 0.1 solar masses of material, very tiny little fraction. We are, you know, few microjansky emission. So I think it's very easy to get fooled in these cases. So the warning we are giving is that for those who are looking at fragmentation in cold clouds, yeah, to be a little bit more careful, maybe just double check before claiming that.
Yes, about the very small grains, are they related with the pHs? And then a second question, yes.
Yes, so when we did implemented the grain size distribution in the models, we took the grain size distribution that basically is the MRN, but goes down to much lower values. So that includes also, yes, the pHs. So if you have a lot of pHs in the gas phase and they keep staying in the gas phase, it's, from the models of Bohr, it's very difficult to form protoplanetary disks.
Yeah, and the second question is, if you remove these very small particles, is there any observational signature that you could test, for example, through the spectral index in the millimeter or in the far infrared? Yes,
so I think we have to make some more predictions of that. So for example, with again for L1544, I didn't show it, but there was a student of mine who finished late last year who actually attempted to do these measurements of, using the dust continuum emission at 3 millimeter and also at 1 millimeter and compare. Of course, again, you know, you have 2 points, but there is, so the conclusion was that in the center of the prestellar core, there is some evidence of increasing opacity, which, you know, you can do it only if you have some maybe growth. I don't know, but you see, I mean, we cannot prove that the very small grains are gone. This is a big question. It's a very important question because the problem with the very small grains is that you see them when they are illuminated, like pHs. But when they are inside the dark cloud, we cannot see them. So I think the way forward is to do, how to say, models again of the dust. And you know, with and without, and try to basically measure, but it's model dependent. So we will need probably many wavelengths to convince people about that.
And what do you think? What is the mechanism to produce this depletion? Is any mechanism already known?
For the very small grain, you mean?
For the very small grain. And what makes hypothetically differences in the abundance of very small grains in different regions to explain the variety of morphologies?
Yes. That's so. My opinion, because again here we are really at the opinion level, is that the very small grains are nothing less than big molecules. So I consider them that, you know, they also can impact on ice, on dust grains, and once they do that, they may get stuck on top of the bigger grains. So they can actually, in fact, this is very interesting also from the point of view of the physics and chemistry of the ice. You can imagine you have like pHs on top of icy mantles. Then you start to, you know, irradiate later on when you have a very rich chemistry. You can have a very rich chemistry. So I think it's just a freeze out effect, like we see for CO. And of course, you can freeze out more or less depending on the volume density and the temperature. So for example, if your cloud, they say the cloud that will form a future stellar system is close to a cluster, so it is warmer, the amount of freeze out will be less, and then I expect that maybe, you know, protoplanetary disk will be either tinier or not present at all. You know, we can make some prediction like that. But if you are in a region that is very isolated, far away from active star-forming regions, like the one that we are seeing, the prediction is that you are going to form a big disk. So I have to stay for more 10,000 years and wait to see if the prediction is correct. But yeah, that, I mean, of course, this is a silly joke, because you can always look at some other more evolved regions, but like, I don't know, maybe in chameleon or, you know, lupus, where there is not much star formation, and actually check this prediction. And it's not just the freeze out, it's also as I said, just a tiny variation in cosmic ray ionization. So if you are close or far away from you know, even a supernova event or something that it can enhance locally the ionization rate, and angular momentum, initial angular momentum, can make very big difference. I didn't show all the crazy disks that Bo can find, but we really have, like, you know, from rings to spirals, all kind of geometries. That it's interesting, because now with ALMA, of course, other groups are seeing these different geometries as well. So, but we are talking about early phase disk.
Okay, I think maybe we can have a last comment or question.
Sure, yeah.
If there is any.
And I can ask, I mean, I can also talk in the afternoon if somebody is interested.
Thank you. Maybe a stupid question, but
no,
if we imagine that we could look at high redshift with the same precision of ALMA, whatever, could we use the same technique to detect pre-galaxy cores? Like
to detect, sorry?
Like pre-stellar cores, but for galactic cores.
You need the super high resolution.
Yeah, but hypothetically.
Yeah, but I mean, that will be very interesting, in fact, because you can then, you know, go in, say, time of evolution where maybe the dust was different. Most likely the dust was different. Maybe it was less than, you know, the amount of dust was less than now. So you expect to have quite different structures, and maybe also very different type of outcomes, you know, in types of disks and things. I think at the moment what we can reach is like maybe 100, well, it depends, of course, how far you are, but for the high redshift galaxies, at the moment, we are still struggling to actually detect, resolve the gas, no, that is seen, for example, in C++, etc. But I say, why not? I mean, we know that in high redshift galaxies, you have much higher densities on average. The average volume density of molecular gas is significantly higher than what we have in our at our epochs. So I would say yes, you have dense cores, and you probably, if you have enough dust, you have again freeze out. Remember that you have the cosmic background radiation that will heat up a bit more, but you know, it will be actually an interesting chemistry. If you have 30 Kelvin, not just the hydrogen but also the oxygen and the carbon move on the surface of dust grains, so you may get actually very interesting molecules. I don't know, I have not done it.
Okay, so thank you very much.
Thank you again.